I'm Amanda McCauley, and this is my Lab 3 presentation. The physics concepts behind this lab were magnetic fields and bar magnets, and the purpose of this lab was to characterize the magnetic field of a bar magnet by determining the field dependence on distance and modeling the magnetic field. The first thing that I did in the experiment was determine the location of the magnetometer sensor on my phone by vertically and horizontally finding the maximums in the x and y coordinates of the magnetic field, since on axis the magnetic field is the largest. Then after I did that, I took some observations that when the sensor is far away from the magnet, it measures a near zero magnetic field in the x direction, as long as you've oriented your phone correctly, like it's possible. And then as long as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So from these general observations and background knowledge, the magnetic field magnitude is proportionally related to distance from the source, as shown by this equation. And when the distance decreases, the magnitude of the magnetic field increases, as I said in the previous slide. So intuitively, I'm expecting my in value to be less than 0. So here's my actual data. I measured the distance of different Bx values. And the only important thing was to start out with Bx is equal to 0 by orienting the phone correctly, and also making sure the right units, centimeters, meters, microteslas, and teslas. When this is plotted, the ln of Bx versus the ln of the position vector, since taking the ln of the equation on the left makes it easier to analyze, so that the value of n, which is what we're looking for, is just the slope, which in my case is negative 2.6. Then the next step was to measure the magnetic dipole moment. And in the original equation, that the magnitude of the magnetic field is just equal to kr to some power. K stands for everything that's constant in this equation. And using the on-axis formula, k is equal to the magnetic constant times 2 times mu. So when I solve for mu using my data, the y-intercept, I get 5.355 coulombs per meter. Then, slightly more difficult is measuring off-axis magnetic field. So I put the magnet on d perp distance away, which in my case was 18.5 centimeters, and measured the y component of magnetic field, and then moved the sensor vertically up the same distance to measure all 3 components of the magnetic field and put them in this data table and compare it to a model using GlowScript. So here's my model with the white cylinder being the magnet and 7 different arrows at different locations showing the magnetic field. I did this. The code behind this is created a dipole function and input my dipole moment from the experiment, which is 5.25, and then I calculated the magnetic field at 6 observation locations. 2 were on axis, 4 were perpendicular. And I showed one example of just calculating the r vector and then using the function and then putting it, displaying it as an arrow. And then it was the same exact process for off-axis, except the vector, instead of having 2 0 components, was d perp 0, which in my case was 18.5 centimeters. And then comparing the model from the experiment, it was about a 12% error. And there were some discrepancies between the y and z components, but this was a very tedious experiment since really small changes in distance drastically affected the total magnitude when I was trying to get it as 100 microteslas. So in conclusion, if I hadn't oriented the experiment to compensate for the magnetic north and had instead laid out the meter stick at some intermediate angle with respect to the Earth's magnetic field, how would the results have changed? The measured Bx would be the field due to the magnet plus or minus the initial Bx reading on the app, which would represent the magnetic field due to Earth, and therefore the readings would be incorrect by unpredictable amounts depending where you started at. And if you were to stick 2 identical magnets together end to end and run the experiment again, I'd expect an even stronger magnetic field due to superposition of both fields, but not necessarily double the values from my experiment, since they wouldn't be next to each other, they would be longer, so some of the magnet would be further away from the phone sensor. But overall, the distance to measure like a magnetic field at 20 Tessa's would be further away, as well as all the other readings.